Hey everyone, I'll be presenting our work on obtaining optimal communication bounds for classic functions in the coordinator model and beyond. This is joint work with Hossein Esfandiari, Wahab Mirokni, David Woodruff, and Pelin Jong. In the distributed model of computation, the input to the problem that we want to solve on is distributed across multiple servers. So one of the examples here is the coordinator model, where there is a coordinator server that wants to solve a problem on some matrix A, but this matrix A is not available to coordinator as is, but is split among multiple servers S. So S servers. So each of the servers holds a matrix A1, A2 up to AS, and the problem that the coordinator wants to solve on is on the matrix A, which is obtained by just adding them all up. So we want to use communication efficient algorithms for the coordinator to solve some problem on this matrix A. So this problem could be a low rank approximation or singular value decomposition or anything else. And in this setting, each of the servers can only communicate with the coordinator and can't communicate arbitrarily with each other. But this is without loss of generality. We can model any point-to-point communication with a factor 2 in the amount of communication, as coordinator can forward anything that server 1 say wants to communicate to server 2. Okay, so this model is without loss of generality and can we can model arbitrary point-to-point communication. In the coordinator model, there is only one input that the coordinator wants to solve problems on, and this input is split among multiple servers, but we can consider arbitrary topologies here. So let's say this is a graph of servers and the edges represent like the communication links that are present. So in this graph, servers 1 and 2 can talk with each other, servers 2 and 5 can talk with each other, and so on. And each of the servers holds a local matrix, what I would say a local matrix. So A1, A2, A3, A4, A5 presented to the respective servers. And the goal in this setting is for each server in the graph to solve a problem on its local neighborhood. Okay, we can suppose that, okay, so the server 2 wants to solve some problem on like the one neighborhood, distance one neighborhood of it. Okay, so the server 2 wants to solve the problem on the union of these matrices A1 union, A2 union, A3 union, A5, and we want to solve such problems simultaneously on the whole graph. Okay, so each of the servers in this graph is going to solve some problem on its one neighborhood. Okay, and it need not be just one neighborhood. We could consider delta neighborhoods for arbitrary delta. So we could consider distance 2 neighborhoods of all the servers in the graph and distance 3 neighborhoods of all the servers in the graph, and so on. And in this setting, in each round of communication, each server sends some messages to its neighbors. Okay, so in the first round of communication, let's say server 2 sends some messages to servers 1, 5, 3, which are its neighbors, and at the same time server 1 sends messages to its neighbors such as server 2 and rest. So we can see that to solve problems on delta neighborhoods, the protocols in this model require at least delta rounds. Otherwise, information from a neighbor which is delta distance away can't reach any server, a server. So the protocols in this model need to take at least delta rounds, and most importantly, we want to simultaneously solve problems on local neighborhoods at all the nodes in this graph. So there is no particular special node, and we want to solve the problems at all the servers in the graph. Okay, so let's look at our results in the coordinator model. So just to recap, in the coordinator model, the input to the problem that the coordinator wants to solve is split among multiple servers. In this setting, we consider the input to be a vector, and each of the servers holds their local vectors x1 through xs, and we assume that these are non-negative. And the coordinator wants to solve some problem on the vector x, which is obtained by adding up all the local vectors. So the problem we focus on is trying to approximate summation I fxi. So we have this long n-dimensional vector that is split across multiple servers, and we want to approximate summation I fxi. So we want to take this arbitrary function, apply to the coordinates of this vector x and add them all up, add the function values up. Okay, so one example of such a function is f of y equals 5 to the p. So this is just the fp moments of the vector x, and this is one of the main problems that we focus on, but our protocols work for general functions f as well. Okay, so and we also assume that in this model there is shared randomness, so all the servers jointly share some source of randomness, and so can jointly sample some random variables that they can use in the protocols. Okay. So to capture like how much communication is necessary to approximate this function sum up to 1 plus minus epsilon factor, we define this parameters called CFS. So CFS is just defined like this: for all y1 through ys, we require CFS to satisfy this inequality. So for comparison, Kannan, Mempala, and Woodruff in 2014 also study a related parameter, but their definition requires f of y1 plus up to ys to be at most CFS times the sum of individual function values, whereas our definition is a bit different. But the main idea behind them is to see how much the local function values capture like the global function value. Okay. So by simple Cauchy-Schwarz, we can see that these parameters are related up to a multiplicative S factor. And for the important case of FP moments, these parameters coincide. Okay. So our theorem is like, given any superadditive non-negative function f that is approximately invertible. So by approximate invertibility, I mean if I give a multiplicative approximation for f of y, then I can obtain a multiplicative approximation for y. Okay? So this is what I mean by approximately invertible. There is a 2-round protocol using CFS times polylog n over epsilon squared bits of communication to approximate summation IF of xi up to 1 plus minus epsilon multiplicative factor. We also show that for a restricted class of functions, we require at least CFS over epsilon squared bits of communication to do this anyway. So our theorem is tied up to polylog n factors, at least for this restricted class of functions. And since FP moment estimation is a special case of this, our protocol solves the FP moment approximation problem in using s to the p minus 1 polylog n over epsilon squared bits of communication, and this is optimal up to polylog n factors in the coordinator model. Yeah, so this is, FP moments are part of the restricted class of functions for which we show CFS over epsilon squared bits of communication is necessary. Yeah. Let's say E1 through En are independent exponential random variables, and consider this global vector. So I obtained this vector by applying this function to individual coordinates and multiplying each coordinate with an independent inverse exponential random variable. Okay. Now if we consider the maximum of this vector, then the distribution of this max random variable is the same as a standard inverse exponential random variable multiplied with the sum of the function values. So note that this is exactly what we want to compute. So if we can somehow compute like the maximum value of this global vector, then we can know some information about the function sum. So our goal is to somehow determine the coordinate in this vector that has the maximum value with low communication. Okay, so note that at servers locally we only have this information, so each server can locally compute E1 inverse f of x1 up to En inverse f of x1 at server 1 and so on. So we want to somehow use these local vectors to compute the location of the maximum value in this global vector. So what we show is, okay, each server j independently samples some coordinates from this distribution. Okay, so let's consider only server 1. We have this local vector a1 inverse f of x11 up to en inverse f of xn1. This defines a distribution over n coordinates where the ith coordinate is sampled with probability proportional to the coordinate value. Okay, we show that if each server J samples CFS over S times polylog n coordinates independently and send all these coordinates to the central server, that is the coordinator, then the coordinator receives I star with a very large probability. Okay, so we can show that the probability that the coordinator does not receive I star is exactly this using the independence of sampling, and we show that this is at most 1 over poly n with a large probability over the exponential random variables. Okay, so to show, we use like monotonicity of this function f and the definition of CFS and the fact that, okay, yeah, and the other properties of exponential random variables. Okay. So what we showed here is, okay, let's say S1 is the coordinate sent by server 1, S2 is the coordinate sent by server 2, S3 is the coordinate sent by server 3. We showed that with a large probability I star is one of them. Okay, I said that each of the servers sends CFS over S times polylog n coordinates. So the number of coordinates received by the coordinator is CFS times polylog n. Okay, so one way to determine what I star is by just sending this union to each of the servers and just asking for the function values at those positions. But that would require a total communication of S times CFS times polylog n bits, which we wish to avoid. We want to do something within CFS times polylog n total bits of communication. So our goal is to find a smaller subset of this union of coordinates that has I star with a large probability. Okay, so if coordinator can find such a small subset, then we can just ask for function values in that subset. Okay, in this work we give a protocol, or we show that using our protocol we can identify such a small subset. So this is done by computing approximations to EI inverse f of xi, just using the coordinates that the coordinator receives in the first round of communication, and by computing these approximations and only by forming the set S by using the coordinates that have a high value of this approximation, we show that such a subset contains I star with a large probability. Okay, then we can just ask for the values of the coordinates at only these positions to the individual servers and then compute what I star is and the coordinate value at I star is using just CFS times polylog n bits of communication and 2 rounds. Okay, so what this does is, given like to compute like the maximum value in this global vector, so, and as we have seen, this maximum value is distributed as is inverse exponential random variable multiplied with the function sum, which is exactly what we want to compute. Now if we repeat this process with independent exponential random variables for 1 over epsilon squared rounds, then we can obtain, using the median, a 1 plus minus epsilon approximation for the function sum. So this wraps our high-level overview of our work in the coordinator model. Let me move on to arbitrary topologies. Okay, so just to recap, in this setting there are servers connected via communication links. So there is no special server here. Each server can talk to its neighbors in this graph, and each server wants to solve some problem on its local neighborhood. Okay, so the server 2 here wants to solve problem on the local neighborhood, like distance 1 neighborhood, and server 4 also wants to solve some problem on the distance 1 neighborhood of it. Okay, so we show that using composable sketches these problems can be solved. So let me define what composable sketch means. So we show that, so the definition of composable sketch is as follows. A sketch construction is composable if, let's say, I have constructed a sketch of A and sketch of B. So A and B are two matrices here. Then just the sketches of A and sketches of B are enough to construct the sketch of the union of these data sets, A union B. Okay, so this is the same definition used in earlier works for composable sketches to solve problems in massive data settings. Okay, So how does composable sketches help us solving in these neighborhood problems? So let's say in the first round, each server just computes the composable sketch on its local dataset and send it to all its neighbors. Okay. So in the further rounds, so each server just does the following simple computation. Each server receives sketches that its neighbors have sent in the previous round and compute the sketch of the union. Because these sketches are composable, just using the sketches that we have received in previous rounds, we can compute the sketch for the union of the datasets that this sketch has been constructed for. And we then just simply send the composed sketch to neighbors again. Okay, so doing this for delta rounds, each server can obtain a sketch of the union of the datasets in its delta neighborhood. Okay, and delta rounds of communication is enough for each node in this graph to solve a problem on its delta neighborhood. Okay, so to solve any problem, if we have a composable sketch construction, then we can do it in this personalized congest model. So in this work, we give a composable sketch construction for LP subspace embeddings. So subspace embeddings are defined as follows. So we have this matrix A. We say that A prime is a matrix approximation if for all vectors x, A prime x is a vector and its pth norm is within 1 plus minus epsilon factor of the LP norm of A times x. Okay, and this has to hold for each vector in the column space of A. And we give a composable sketch such that sketch of A can be used to construct a matrix A prime that has this property. Okay, and our composable sketch also has a size of d to the max p over 2 plus 2 comma 3 times polylog d over epsilon squared bits. So here d is the number of columns in the matrix A, and for p equals 2, which is like the most commonly studied case, we can obtain composable sketches of size d squared times polylog d over epsilon squared bits. Okay, so yeah. And again, as in the coordinator model where we use shared random variables E1 through En to correlate the randomness across the servers. Here we again use shared fully random hash functions across all the servers to correlate randomness, and our composable sketch construction simply implements LP sensitivity sampling. Okay. So the sketch of A is simply a subset of rows of A sampled according to LP sensitivities. So given a matrix A and a row A, the LP sensitivity of this row A with respect to A is defined as this. So this is what we call LP sensitivity. And LP sensitivity sampling shows that if each row of this matrix A is independently sampled with probability like proportional to sensitivities and with a multiplicative factor, then the sampled rows can be used to construct an LP subspace embedding with a large probability. Okay. So this is what the sensitivity sampling says. So our goal is to construct a composable sketch that implements this sensitivity sampling. Okay. So for that we require the use of these fully random hash functions. So H is a fully random hash function that can map rows to independent uniform random variables in the interval 0 to 1. So once we have this hash function H, we are simply, and to construct a composable sketch of matrix A, we are going to simply keep all the rows A with hash values that are smaller than this multiplicative factor of the LP sensitivities. Okay. If the hash function H maps rows to independent uniform random variables, then we can see that the sketch, which is just a subset of rows with the hash values smaller than C times tau A times d log d times epsilon to the minus 2, simply implements LP sensitivity sampling. Okay. Now let's consider our two arbitrary matrices A and B and their corresponding sketches that are constructed using the same hash function H Okay. A key property of sensitivities is the monotonicity. So if a matrix A has this row A, then the sensitivity of A with respect to matrix A is larger than the sensitivity of A with respect to the union, so A union B. So if there are some, yeah, the matrix formed by just the union of the rows. Now let's define the sketch of union. So by definition, sketch of this union is simply going to be those rows in A union B with sensitivity smaller than, with the hash value smaller than C times the sensitivity with respect to A union B times d log d times epsilon to the minus 2. Okay, and the monotonicity shows that the sketch of A union B is going to be a subset of the union of the sketches A and sketch B. So at least the sketch of the union has to be the subset of this union. Okay, but importantly note that we need to be able to compute this sketch of A union B using only sketches A and sketch B. So currently the definition of the sketch uses the sensitivities with respect to A union B. So we need to figure out if there is a way to compute this sensitivity with respect to A union B of the rows in the sketch to compute the sketch of A union B. Okay. So the main question is, how do we evaluate this LP sensitivity of rows with respect to A union B just using sketches? Okay. So what we show is the sketches themselves can directly be used to compute a sensitivity. The sketches themselves can be used to compute a subspace embedding, which can then be used to compute the sensitivities. Okay. So let's say we have these sets A and B of rows, and let's define a new sensitivity. Okay. So I'm going to define for rows that are present only in A, this tau A value to be sensitivity of A with respect to A. For rows that are only in B, I'm going to define tau B to be the sensitivity of B with respect to matrix B. And for the rows in the intersection, I'm going to define the tau C to be just the minimum of the sensitivities with respect to A and B. So our main observation is that this tau upper bounds the sensitivities of rows with respect to A union B. Okay, so if we consider just this subset of rows C such that the hash value for that particular rows is smaller than C times tau C times d log d times epsilon to the minus 2, then this is also an LP sensitivity sample of the rows of A union B. Okay, and importantly, this can be computed just using sketches of A and sketches of B. That is, this subset of rows can be computed just using sketches of A and sketches of B. Okay, and since we are able to do LP sensitivity sampling of A union B just using sketches of A and sketches of B, we can then compute a matrix M that satisfies this guarantee, because we can compute a LP sensitivity, LP subspace embedding. Okay, so using this, we show that we can compute approximations to sensitivities of rows with respect to the matrix A union B accurately. Okay, that lets us compute the composable sketch of the union A union B just using sketches of A, sketches of B, and this matrix M that we compute. So a key issue in the argument that I presented is that the same hash function h is going to be used to compute the subspace embedding M and also to implement the LP sensitivity sampling of A union B. So this doesn't satisfy the condition required for sensitivity sampling anymore. So the sampling of each row is not independent. So what we do is to decorrelate is to use two hash functions. So instead of just one hash function, we use two hash functions h1 and h2, each of them mapping rows to independent uniform random variables. So we use sketch of h1a, sketch of h1b to compute this subspace embedding M, and we use sketch of h2a, sketch of h2b to compute sketch of A union B with respect to this hash function h2. Okay, so this correlates, and we can then show that The sampling we perform is basically sensitivity sampling, and so the subset of flows that have been sampled can be used to compute NLP subspace embedding. Thanks for listening to the talk.